All right, so now this is going to be a different, this will be mainly on the blackboard, and I apologize if some of you have seen some of this because some of it's fairly basic, but I think it seems like a good idea to go back to, to, to basics. So if you, um, mostly I'm going to talk about barotropic dynamics, but I'm also going to talk about gravity waves because that's an important part of the turbulence in the atmosphere, and I know that also some of the speakers next week in the ocean are going to pick up on internal gravity waves, so it's worth thinking about that. And it gets to the issue of balanced and unbalanced flows. So the the canonical model for this in terms of PDEs is the shallow water uh, equations on the F plane. You all know what the F plane is. It's the planar approximation to the rotating sphere. So constant Coriolis parameter. So it means that we don't have Rossby waves, but we it's the simplest setup. So we have and it's a very nice model mathematically, and it's also importantly I'd say it's it's analogous, at least for the atmosphere. I guess in the ocean it's maybe a more of a natural model. In the atmosphere it's not a kind of intuitively natural model, but it's analogous to the horizontal component of the primitive equations. That's a hydrostatic equations in isentropic coordinates. Isentropic means constant entropy or constant potential temperature. So you can think of the stratified system as being a set of layers, isentropic layers, and each one looks like shallow water. So it's a very nice model. And in fact, when people develop dynamical cores in the atmosphere, they actually always have a shallow water version of those cores. That's always the first test that they do because it has fast waves before they go to the primitive equations or even compressible actually now. So we have du dt plus the advective nonlinearity u dot grad u plus f z cross u is minus g grad h, where h, so this is the horizontal velocity and h is the height, and then we have the equation for h for the height. I think you've all seen this. Make sure I don't make typos. So the first thing that you do, we talk about fast and slow. What do we mean by that? Well, if you linearize about a state of rest, with h being a constant. So of course everything here is a function of x, y, and t, but we just take h to be a constant, which would be your mean depth, and you substitute the ansatz that everything varies like exponential of I k x plus ly minus omega t. So this k is an x wave number, L is a y wave number, omega is a frequency. The system is autonomous in time, and it's got no dependence on x or y. So you can assume always these kind of solutions. And then if you solve that, I think you probably all solve that at some point. If you haven't, it's a good exercise, but it leads to a cubic equation because you've got three. Sometimes so u has two components, it's x and y, so we have three equations. You get three roots. The first root is a zero root, or omega squared is f squared plus gh. Kappa squared, where kappa squared is k squared plus l squared. So we have three roots here. There's this the zero frequency root, which in this case is just we call the vortical. I mean, nothing's happening here in the linear case. If you did this on the beta plane, you would get Rossby waves. And then these are inertia gravity waves. And we see that the character of the inertia gravity wave depends on the wave number, kappa. So when we have kappa being very small, we get that the I shouldn't say, I should never write that, f squared over gh. Then we get a rotation dominates. So these are large, small wave number, large scales, and kappa much greater than f squared over gh, and then we get gravity dominates. So in the latter case, we just have surface gravity waves. If you have a non-rotating water with a free surface, you get surface water waves. In this long wave limit, you get the rotation case, and importantly, the inertial gravity wave frequency is always greater than f. So we have a low frequency cutoff. So that's important because then there's obviously a clear bound to the lower frequency. There are problems like the compressible flow problem where this isn't true, and then you get sound waves which don't have a low frequency cutoff, and the famous Lighthill problem of sound generation by turbulence. Even if you have low frequencies in the turbulence, you can generate low frequency sound waves by going to very long wavelengths, but there's no direct coupling. So it's not analogous. I mean, this is a point where I hate to disagree with Michael McIntyre, I guess, but I probably don't really fully understand his point. But the analogy with the Lighthill radiation isn't exact. There is a very important difference, that there's a low frequency cutoff in the Rossby wave case. Okay. Oh yes, sorry. Yes, thank you. Just for the record. Okay, well, this is linear, and that's not what we're interested in, of course. So heuristically, you can generalize these frequencies. So of course, if you have the advective nonlinearity, that gives a Doppler shift. So we can introduce a Doppler shift to the frequency, which would be something like u kappa, where u is some characteristic velocity. And then I get that omega naught over omega ig, if we allow for this, we're not quite in the linear case now, we allow for the Doppler shift case, and I get, of course, a u kappa in the numerator, because that's just about 0, and in the denominator u kappa, and I guess it must be root of f squared plus gh kappa squared. And this will be small. It's easy to show. This will be small if and only if quantity that we'll call epsilon, which is u kappa over this thing, f squared plus gh kappa squared, is small. So as long as this parameter here is small, then we're going to have a time scale separation, and even with nonlinearity. As to say, this is heuristic, but it means that we have a time scale separation between. The point is, we can talk about fast and slow. I mean, this is ultra slow, if you like, but even when you allow nonlinearity, we still have the scale separation. We still have a low frequency cutoff here, and we can talk about fast and slow dynamics. So implies separation in time scales. Fast and slow dynamics. Okay, so there's a couple of dimensionless parameters which are important. So one is the Rossby number, and that's u kappa over L, or f. It's sometimes written as u over FL, but kappa is just inverse of the length scale. And that's the Rossby number. And the Froude number. Froude number is used in a lot of different ways, and confusingly, the Mountain wave people use an inverse Froude number, so that really confuses it. But I think we would usually, and there's something called a rotational Froude number, which is something else entirely. But the Froude number should be, I mean, at least my understanding is it's the ratio of the velocity to the gravity wave phase speed. So it's like the Mach number. It's analogous, and so this is the Froude number. And importantly, also this generalizes to a vertically stratified flow. I think Hank was mentioning hierarchies of models. It's a very, very important concept, I'd say. And so something, although I'm focusing on these simple systems, I always have an eye on connection to the primitive equations. And in some sense, if I couldn't generalize what I was doing to the primitive equations, I wouldn't be comfortable. As an aside, a lot of mathematicians are very interested in a system called the semi-geostrophic equations. It's got some beautiful mathematical properties, but none of those properties hold for quasi-geostrophy or the primitive equations. So I guess that's where pure math departs from applied math, maybe. Because for me, unless it's a property of all the systems, unless you can trace it, which is linked to a symmetry and so on, I lose interest rapidly. Anyway, this you can easily come up with a stratified version of the Froude number, which has an internal gravity wave phase speed rather than a surface gravity wave phase speed. Okay, so then this, if you with a bit of algebra, you can. I just erased epsilon, didn't I? But oh no, sorry, it's here. So it turns out that epsilon is Rossby times Froude over square root of Rossby squared plus Froude squared, which is a nice symmetric expression. And the interesting thing about this is that so epsilon is small if either Rossby number is small or the Froude number is small, even if the other one blows up. So, for example, at the equator, if the f goes to 0 and the Rossby number goes to infinity, but if the Rossby number goes to infinity, it's not a problem, because then you just get Rossby number here, which cancels the Rossby, and you just have Froude number. And there's a classic theory of tropical balance from Charney in about 1963, which is based on this low Froude number balance. So this is a sort of a seamless way to talk about balance, which both includes this small Rossby number regime and the small Froude number regime, which is why I like it. Or you could, I guess you don't generally have the Froude number going to infinity, but so that you can see that both regimes are important here. Yes? I'm being general here because this is just heuristic. I'm not, doing any formal bounds or anything. I mean, classically, what you would use is a square root of the kinetic energy or something if you were going to have some kind of a norm. Oh, h is the mean depth. Yeah, there's no problem with the h. I mean, the thing is, who was telling me they'd met Nathan Paldor? Yeah, I had this big argument with Nathan. He just doesn't accept that you're allowed to. Have you had this argument with him, Brad? You should only have non-dimensional parameters that are physical constants. Oh yeah, well try him on that one. So it is very common, in Podolsky and all this stuff. You have a U and a K, and a mathematician would say, "What is U? What is K?" Those are very good questions. So you okay. Well, there are certain parameters like F, which is rotation of the Earth, G is gravity, H is the mean depth. If you fill your tank of water, there's a certain amount of depth. It's the mass. So there are certain constants that are parameters of the system. Then there are certain internal things, like what kappa is something internal. We're talking about a certain length scale, and U is a velocity. What do we mean? So of course, if you're going to do anything rigorous here, you have to define what these quantities are. And usually U would be the square root of the energy, and L would be some length scale defined, say a ratio of energy over entropy square root or something. You'd have to have some way of defining these quantities. But just heuristically, h is, as I say, the mean depth of your fluid. Oh, I see what you mean in terms of a practical. Well, I mean, I guess an oceanographer might use depth of the thermocline, for example. Is to say, in the atmosphere, we don't really use shallow water in practice. I'm not aware of people that would use it in a quantitative way. It's used as a very important numerical test bed, as I said, but I don't think. I guess there are arguments for MJO where people try to use equivalent. So there's something called equivalent depths, and there's analogs of shallow water that are used in the tropics. But then that gets way more complicated because it's actually not really. I've never understood equivalent depth. But other questions? Okay, so essentially, I said that whether rotation or stratification dominates depends on the kappa, and it's also you can see it in the ratio here. Froude over Rossby determines whether rotation or gravity dominates. Because Froude over Rossby is F over kappa root GH, and that's just L over this L sub R, where LR is defined to be the Rossby deformation radius, square root GH over F. So that's a physical length scale given your parameters. And basically, if the length scale is large compared to the deformation radius, then you're in the the Froude number is sorry, if the Froude number is large, yeah, if the Froude number is small compared to Ross, do I have this right? Yeah, if L is much smaller than the length scale, then you're in the case where the Froude number is much smaller than Rossby and vice versa. But typically in classic so there are different regimes, and actually in the oceanography, people are definitely interested in the L much greater than LR regime. But in the atmosphere, LR is a pretty big scale. It's 1,000 kilometers or so. So if you want to it could go to the primitive equation. So typically in what's called classical quasi-geostrophic scaling, R naught is taken to be equal to FR. So that means that the rotation and stratification effects are comparable. So that's what I'll do here. Oh, it isn't stratification. Well, it is very stratified because you've got air over water. Okay. Gravity, I should say. You're a purist. Okay. So now, yes? Yeah. Right. That's why I wrote it down, because in the back of my mind I'm thinking stratified, but yeah. So it's the same physics. Of course, you get different phase speeds and things like that, but you still have it just becomes internal waves. Okay. So now what we have to do is non-dimensionalize the equations. Okay. So I write them again. So we non-dimensionalize. Of course, there's no approximate. These are the full equations. So non-dimensionalization does not involve any approximation. It's just rewriting the equations. The approximations come afterwards. So we have to pick some scales. And this is where you can be a purist and just insist on picking scales that are physical parameters, which I admit is probably the correct thing to do, but you can save a lot of time. But then if you do that, you wind up having to go to fifth and sixth order to make things settle. So we just do the usual GFD approach, where we'll say that there's a characteristic velocity u, a characteristic length scale L, which we'll take to be LR because there is actually a physical length scale, and then for time we have some choices. Now we're going to seek slow solutions here because we're looking for balanced states. So we're going to actually pick a time scale, the slow. So we're going to pay based on advection, and I'll show how this works out in terms of the gravity waves in a second. So the advective time scale then is just L over U or LR over U. Now for the height, of course we have a mean depth. So you have to have the fact that there's a mean depth in there. So what we do is we'll just mean depth and I'm going to put a Rossby number scaling in here times eta because we expect that the perturbations from the rest state will be of the order of the Rossby number. And as I say, if you can pick anything because there's no assumption made, and well, there is sort of an assumption here, but you'll see I mean, at this stage, it's just rewriting the equations. So if you do this, you can see that this term is going to give us something that's going to have a u, obviously, from the u, and then from the time scale, but is 1 over time, so we're going to get a u squared over LR. This term is also going to give us a u squared over LR, because a u times a u over an L. That's not surprising because we've chosen the time to be advective, so these should be the same. This gives us f times u, and this gives us, well, the grad h, of course, the constant is 0. It only depends on the gradient, so we get a g times the Rossby number. That's it, g times the Rossby number, and the Rossby number is I'm sorry? H over, sorry, oh yes, there's an H there too, that's right, GH, yeah, Rossby number, so that's U over FL. So, oh, LR, oh yes, right, so then, but then you, oh, there must be a, what am I doing wrong here? Oh, LR, yes. There's no F, what am I saying? The grad H gives 1 over LR, and what am I doing? And the Rossby, yes. So maybe I want to keep the Rossby over LR, don't I? This is the problem of doing it on the board. Okay, so and then so actually this so where does my what have I done wrong here? Sheet. Because there should be a 1 over Rossby in front of that. G. No, but that's the gradient gets rid of the 1. Yeah. I'm a bit. Shoot. So what have I done wrong? Oh, sorry. No, this is right. I do get a 1 over in front of this. That's right. So this is fine. Okay, so this is so Rossby is U over F. Well, let me just leave this as Rossby for now, and then here we're going to get an H Rossby over the time. So that's an U over LR, and then this is also going to be, well, it's going to be the same thing, except now we have an H in front of it. Sorry, the time dependence. Yes, no, that's right. But now we have an H. Here we have an H del dot U because there's a constant here, and then this is going to be U over LR. So actually, we have an H. Bring that down. We have an H U over LR. So we have one. So we so we have a term here that actually is large, whereas this is order a Rossby number. And there's, yeah, that's it. So we have a Rossby number term in a. So we see that this is an this only has maybe the simplest of the powers of u. So this has a u squared, this has a u squared, this has a u, this has a u. This has a u, this has a u squared. So if we write this all out, and divide to you get, so this is now non-dimensionalized. You get 1 over Rossby in front of z cross u plus grad of eta, and then d eta dt plus del dot eta. So if we have the nonlinear system, we have this term, and then we have a 1 over Rossby del dot u equals 0. Okay, so this is what happens if you non-dimensionalize, assuming this advective time scale. So I guess so if the Rossby number is small, then basically what we're forced to take this term to 0 and this term to 0. So we need, first of all, z cross u is minus grad eta, which implies that v is u is minus d eta dy, and v is d eta dx, where I'm writing a vector u as components, scalar u and v. And so this is geostrophic balance. So you're used to seeing geostrophic balance with pressure if you're used to another form of the equations, but in the shallow water course, the pressure is related to the free surface elevation. High eta means high pressure. So this is a geostrophic balance, that the winds are balanced by the pressure gradient, and you don't see the Coriolis parameter because it's being absorbed in the non-dimensionalization. And then from the other equation, we have the divergence is 0. So, or equivalently, if we often write a velocity in this form z cross grad of a stream function plus the gradient of a velocity potential, and so in this case we have psi is equal to eta and chi is equal to 0. So the rotational flow has a stream function given by the height, that's geostrophic balance, and the divergent flow is 0. And those are our constraints. So basically, this is the simple definition of these balance conditions in the shallow water system. But there's something a little funny here, maybe, because we began with 3 equations here, because we have 2 components of velocity here and h. We have 3 constraints here. Well, that's a bit of a problem, isn't it? We've got 3 equations and three constraints. So I don't know how to get around this problem. If I satisfy, are these independent constraints? No. So if I satisfy these, if I'm on the F plane, things get complicated on the beta plane, so another reason not to do beta. If I'm on the F plane, if I take the divergence of this, I get 0, because it's coming from the curl. So actually these are redundant. There's only 2 pieces of information here, actually, as you can see from the fact I've been able to specify the flow from 2 vector stream functions. So there's only 2 independent constraints, and if I so these are only so what you can do, you can go back to these equations and you can eliminate the 1 over 1 over Rossby terms. And that gives you an equation that looks like this: d by dt plus u dot grad dv dx minus du dy minus eta equals 0. And that should be recognizable to you as the quasi-geostrophic, or QG, potential vorticity equation. So are you comfortable with potential? Who has not heard of potential vorticity? Okay, that's good. So it's a generalization of vorticity to allow for the stretching in the system. So why we have this eta term here? No, but I mean, if I just eliminate this, if I just mathematically get rid of the, I can derive this equation from these. That's all I mean is so we actually had three. So we had three equations, and now we have actually two constraints because it's not normally three constraints. Once you satisfy these, and this one follows. So we have two constraints. So two diagnostic relations and one prognostic equation. So we now have our first order. This is now a closed first order in time equation. Yep. Yep. Trial and error. It's an art, as Hank would say. I mean, asymptotics is an art. I think for these problems, it's always in a way reverse engineering. But in some sense, there's no approximation made by that. So right, because it's just a transformation of the equations. So I don't know the exact answer to your question. It'd be worth trying and going through, but you're going to find that there are going to be some unbalance. I think what you're going to find is that one of these terms is going to blow. Actually, I think what's going to happen is that's going to come up on its own at the leading order or something. So you're going to be forced to find that it's coming in at the lower order. So what you generally find if you do that is that you is that the leading order of this guy is going to be 0, and then you just pick this up at one higher order in the Rossby number anyway. I haven't done an expansion, but if you start doing the asymptotic expansion, if you've sort of guessed wrong, all that happens is you have to do more work, but you're going to get to the same thing in the end. The key assumption is that I'm looking for a slow time scale. That's the place where the assumption comes in. Other than that, there's not really. I don't think there's any assumption here. Well, and the Rossby fruit number being the same. Sure. Yeah. Oh yeah, yeah. So the original h was h 1 plus Rossby number times eta. So if I didn't put the Rossby number here, then I would find that I would get this term on its own at like a 1 over Rossby squared, and I'd be forced to pick it to be 0 at the leading order because there wouldn't be any other term that would balance it. And then I would just come in at the next order, and I would wind up in the same place. So it doesn't really matter. But there is a certain art to making all these things work out. And actually, I guess, well, I shouldn't, I won't get into another. Happy to talk over lunch or some wine about the philosophy of using asymptotics. Okay, so we have a closed first order in time equation. I should say one thing. You've taken a curl here, so it's not quite the same equations as the original equations which were in a velocity. So if you do that, you need an extra boundary condition. So you need an extra equation on any lateral boundaries. Because if you differentiate the equations, right, like when you have a viscous boundary layer, when you differentiate the equations, you're going to need extra boundary conditions. And you can see it immediately because if you want to solve for the velocity from the potential vorticity, you're going to need boundary conditions. So this is conservation of circulation, Kelvin's theorem. But I won't go into that. Of course, if you have a doubly periodic domain, these things don't arise. Now, so the fact we have a single equation is no accident because we had a one slow frequency. So say existence of a single slow equation since we had a slow mode or a low frequency, in this case 0 frequency linear mode. Okay. Now this is working through, in the cumbersome way that you generally find it in the books. But this is a very general principle. It's called elimination of fast variables, and it's used in a lot of areas of physics. So I'm just going to write a kind of a general thing, because of course the same philosophy applies to any system that we look at in atmosphere or oceans. It's important that, as you probably know, that this is quasi-geostrophy, because it's not exact. The system is not completely geostrophic. If it was exactly geostrophic, there would be no flow at all. And so the reduction is, so we've had a reduction here from three equations to one. The same thing happens in the primitive equations, or the Boussinesq equations, which are widely used. And that's in that case. In this case, it's this is because we've eliminated the inertial gravity waves through constraints. So we've basically taken the 2 degrees, the 2 time evolution equations, and we converted those to diagnostic equations. The same thing happens in the primitive equations over the Boussinesq equations. Just now we're talking about internal gravity waves. And the same thing happens for a compressible flow. Where you have sound waves, and sound waves like inertial gravity waves or internal gravity waves come in pairs. You have it's an omega squared. You have frequencies in two directions, so you eliminate the sound waves. And if you really want to do it, you can do it in compressible stratified flow, and you get 5 roots, and 2 of them are sound waves, and 2 of them are inertial gravity waves, and 1 is the zero frequency mode. Okay, so as a way of, there's a number of ways that you can generalize this kind of approach, and the one I prefer is called the slaving approach. So the idea, we recognize that this is not exact, because if I plug the QG solution into the shallow water system, I don't get a solution, right? So very important that the QG solution is not an invariant manifold, or does not live on, I don't know the right terminology. It is not I should say is not invariant with respect to the shallow water equations. So that's why it's quasi. So then the question is, can you do better? And you can introduce a perturbation expansion. And the simplest way to do this is we can seek a slow manifold, a so-called slow manifold, by slaving. See, in this case, we say that the fast variables are slaved to the slow variables. If you know the slow variable, then you know the fast variable. The fast variables are just 0, actually, in this case. But slaving to the slow variables, sorry, fast variables. It turns out if you do it in a kind of a straightforward asymptotic expansion where you expand everything, you wind up that your equations blow up. You wind up that your leading order system just behaves nonsensibly if the slow dynamics is chaotic, and the slow dynamics is chaotic. So this is talked about in this paper by Warren et al. Some of you may know the Woods Hole GFD program and the Walsh Cottage. This was written in the summer with a lot of, I think we overwhelmed the recycling department in Falmouth that summer, but a bunch of us were sharing a cottage close to Woods Hole. So we're going to just write this symbolically this way. So if we look at this, we have we're on a certain time scale, and you can see, and this gamma is an invertible operator. So this is a very general representation of the dynamical system, but it's a dynamical system with two time scales. So we have the so-called slow variables, which are evolving on the order 1 time scale, and they're going to depend on the slow and the fast variables, and of course on epsilon. And then we have the fast variables, but we call them fast because there's 1 over epsilon here, just like we had in the shallow water system. So this is an invertible operator whose spectrum gives the fast frequencies. If I wrote this operator for the full system, it wouldn't be invertible because I have a 0 frequency over here. But because I pulled off the fast frequencies, it's invertible. So if I go back to if I just go back to a fast time scale, so on the fast time scale, tau, we just get df d tau plus gamma f equals epsilon big F, and ds d tau equals epsilon s. So you see that on the fast time scale, the slow variables don't evolve to leading order. They have a 0 frequency, and the fast variables give us the frequencies, the inertial gravity wave frequencies. So you can see how it maps onto the fast system. But the idea here is we're going to see if we can find some invariant manifold that will be always slow. And so what we do is there's an ansatz that we just let f be some function of the slow variables in epsilon. Sorry, you all of this. We're going to call this the slaving relation. And then we're going to expand f. So f is f naught plus epsilon f1 plus epsilon squared f2, and so on. But we don't expand s. That's the key. So we slave to a slow variable, and we try to find it. And actually, it turns out this is linked to a renormalization theory that Timon has used, and so on. So you can justify this, at least in simple systems. So if we do this, actually everything falls out very simply, because if we look at order 1 now, what's the leading order solution? Well, we just have that f, if we expand this out, we're going to have the order 1 term here has a 1 over epsilon that's unbalanced. And since gamma is invertible, f must be 0. So the leading order solution is that f is 0, and then I can substitute f in here, and I just get ds dt is s with s, 0, and 0. So this is the leading order dynamics, and it should look recognizable to you in the sense that these are the normal variables for the fast waves. Those are just set to 0, like divergence and the geostrophic imbalance. Actually, well, I'll show that in a second. Actually, that isn't obvious yet. So we get a closed system that's just in terms of the slow. But if we go to order epsilon, now we substitute in here, and we're going to have an epsilon f1 here, and the epsilons cancel, so I'll get it. But df2, this is just d by dt of f0, and f0 is 0. So this term goes away, but I have something from here, and then I get a piece from here. So I get that f1 is gamma inverse times f of s0, 0. And so you can see that actually now I get something non-zero. I'm going to find that the fast variables are non-zero, but there's non-zero in a way that will it'll be balanced by the term here. But because this doesn't have a 1 over epsilon in front, this is coming from the order 1 solution, so I can substitute in here. And if I want to seek ds dt now, I just get s f1 and epsilon, and I have to expand this and keep only to order epsilon terms. So you can go on, and actually, you might think that you would have to stop at the next order where the df/dt comes in, but because df/dt always comes in at one order lower than the f here, you're using a lower order version, the lower order expression that you've already solved for. So at the order epsilon squared, there'll be a d by dt of f1, but you can write that in terms of d by dt of s. So everything's closed. So you can get a this goes on ad infinitum in principle. Right. I will go to some slides in a second, but just before I do that, let me just. So this is the basis of balance theory, and just for your interest, this is what would be called Charney Balance in the meteorological literature. But I'll show the equations for that. So in GFD, the thing is a slow equation. So you could say, what's a slow variable? Well, we always know one slow variable because a slow equation is always provided by the potential vorticity. I mean, the Bible for that is this a review paper by Hoskins et al. In 1985, Quarterly Journal of the Royal Met Soc. But you know that there's a potential vorticity in the compressible stratified system, so it's just a property of any model we would ever use, basically in GFD that has rotation is going to have potential vorticity. In the case of the shallow water equations, the potential vorticity is f plus z dot curl of u over h, and that's when we non-dimensionalize, that gives us an f 1 plus Rossby number z dot curl of u. So you get a Rossby number in front of the vorticity, and you get a Rossby number 1 plus Rossby number eta in the denominator. And if you expand that out, you get f over h, big H, 1, so there's a constant, which doesn't, in this problem doesn't matter. And then you get a Rossby dv dx minus du dy minus eta, plus higher order terms. Missing a bracket. Oh, sorry. So this is expanding out in the Rossby. Of course, you have an infinite expansion there from the denominator. And this is apart from this, from the constants. This is just the QG potential vorticity. So we see that the quasi geostrophic PV that we got was just the leading order approximation in a Rossby number expansion to the full PV that you get from the shallow water equations. And the fast variables are the divergence we've already talked about, and the other is the del squared psi minus eta. So this is the geostrophic imbalance. So basically, the geostrophic balance condition is imposed by this condition, by psi equals eta. That is geostrophic balance. So when this is 0, that imposes geostrophic balance. If that makes sense. So these were the two equations. These were the two constraints that we derived, that geostrophic balance and non-divergence. And then we have this PV equation. Okay, now I don't see how far we. So now you can actually carry this. Like most, cool things, it gets complicated when you try to work it out in practice. But so this symbolic representation of f and s was very simple here. But if we try to apply it for the shallow water equations, and this is what's in the Warren et al. Paper, and actually the definition of Q is slightly different. So little q. So we have f over h 1 plus epsilon q here. And so q is actually del squared psi minus eta over 1 plus epsilon eta. So that's the q. But it's equivalent. I mean, it's an exact transformation here. And then if we write the equations out, we get, of course, for the potential vorticity, it's pretty easy. It's minus a Jacobian of psi and q. That's the advection by the rotational flow, and advection by the divergent flow. And that's true at all orders. So the idea about this is that you'll always have a PV equation, but what you'll get as the psi and the chi will depend on the order of the approximation. And if you write an equation for the divergence, and write an equation, and omega is del squared of psi minus eta. So this is this geostrophic imbalance. We get, like we expect for the fast equation, we get d by dt is minus omega over epsilon minus. I'll just write it down. Don't necessarily write this down. It'll just make you tired probably. It's all in the Warren et al. Paper. So it's a pretty complicated expression, and for the geostrophic imbalance, we get del squared minus 1 d over epsilon minus Jacobian psi del squared psi minus del squared del dot del squared psi grad chi plus. This is kind of pointless, isn't it? But just to check that you're on the right track, you should look for the fast system. You should always check to make sure you haven't made a mistake somewhere. So the fast system, we rescale time, which means that the epsilons here go away, and you put epsilons in front of the right-hand side. So the right-hand side goes to 0 at leading order, and you have partial dt d tau minus omega is 0. D omega by dt is minus del squared minus 1 d is 0. So that says that the second derivative of d with respect to time is d squared by dt squared is equal to d omega by dt, which is equal to del squared minus 1 times d. So we see that we have a second order in time equation for d, and we get that omega squared is 1 plus kappa squared, which dimensionally gives us our f squared plus GHK squared. So the fast system is still here. It's just in this form. But you can see that I'll just yeah. But now if we look at the leading order and the next order, we see that order 1, well, we get, so of course I'm expanding. Omega is omega naught plus epsilon omega 1, etc. And the same thing for d. Well, and so for all variables except for q. So order 1, we get that omega 0 equals 0, and that tells us that psi 0 is equal to eta 0. And d0 is 0, which tells us that chi 0 is 0. So this is just geostrophic non-divergent flow, and the dq dt is just minus Jacobian of psi naught q, and the definition q is just del squared psi naught minus psi naught. So that's what we had already without doing the expansion formally. But the nice thing about this is you can go to higher order, and so now we get omega 1 is 2 Jacobian of. So although this looks like a mess, if we go to, so we get omega 1 times epsilon cancels the epsilon, but here we use the leading order, and the chi's are all 0. So this term goes away, this term goes away, this term goes away. We just have that term on the right-hand side. and we get twice a Jacobian of psi naught del squared. Sorry, what am I? Psi naught x, psi naught y. And this is, you may recognize, so this is the geostrophic imbalance, and this is known as the nonlinear balance equation, typically. For example, it would give you a gradient wind. I think you probably all looked at the gradient wind approximation. So when you correct geostrophic balance to take account of the flow, you get this term. And then the other equation is del squared minus 1 del squared chi is Jacobian of psi naught del squared psi naught. And this is the QG omega equation. So it's called omega because in pressure coordinates, meteorologists write omega for the vertical velocity, not the omega frequencies. So we use W in geometric coordinates and omega in pressure coordinates, and you can see that in the primitive equation system, a divergence by the continuity equation is linked to the vertical motion. So this gives you equation for the vertical motion, which actually was used. I learned this at MIT in synoptic lab, plotting out using the omega equation on charts. So, and I think it was still used in those days, at least, by synoptic forecasters. And then you have a little more complicated equation for the PV, because now this eta term from the denominator comes in. So you have this equation for PV. Okay, so I'm going to go to slides now. That was convenient because I finished on the right board. Can we, yeah. Oh yeah, thanks. Right, so this is just all the stuff I went through. Okay, so this is I just cut and pasted these in. So I've already just gone through this on the board. This is the shallow water system, and actually we got all the way up to order epsilon. So the nice thing is you can go as far as you want, and order epsilon squared, it's actually not so bad. You have a advection of PV, and to get the stream function, you have to solve this equation, and to get the velocity potential, you have to solve this equation. The only problem is the functions are a bit complicated. So I don't think in practice you would tend to go, there was a lot of interest in using balanced models actually practically to in the 80s to actually solve problems quantitatively, but especially you think of trying to solve this numerically with multi-grids and everything, it just is hopeless. So what people do is they just run the primitive equations with heavy time filters, sadly, to get rid of the fast waves. But but it's important to know that this can generalize, and as I say, these things can be implemented in diagnostic relationships. Now, so I'm going to talk, actually, I wasn't going to include this, but Hank has talked about dynamical systems, and so that's nice. I'll do a bit of a segue into dynamical systems for this problem, and it's called the slow manifold problem. So I said we can seek a slow manifold. Let's just assume it exists and try to find it. So Lorenz wrote a very famous paper published in '86 on the existence of a slow manifold. So, like all Lorenz papers, I guess it's beautiful, but I do encourage you to read that because his reasoning is just immaculate. But he obviously wasn't completely satisfied because 2 years later he wrote this paper. And then a few years after that, he wrote this paper. So it's an interesting field. And so I was motivated, actually, and so that's the one connection. The other connection to Hank, I guess, is that I had almost my first PhD student in Toronto as a Dutch guy, Onno Bokhoff, and so we looked at the slow dynamics problem in in this 86 paper. So Lorenz, of course, has lots and lots of lower order models, and this is one of them. It's a 5-component model. Interesting thing is it's one of his few models that's not dissipative. So this is the way that he wrote the model. And it comes from a vorticity triad. So you may recognize these equations if we ignore the b's here. These are the equations for a vorticity triad, interacting triad. And then these are from a gravity wave. So it's basically a gravity wave, inertial gravity wave, coupled to a vorticity triad. And the coupling comes through this parameter b. And it's a Hamiltonian system, and actually even in this 5-component form, we'll talk about that a bit tomorrow. I guess it's what's called a non-canonical form of a system, because canonically Hamiltonian systems are always even dimensional. This is a Hamiltonian, and this is the other invariant, which is called a Casimir. So as I say, if it's just b equals 0, then actually, so if c is a constant, so you can reduce this now down to 4 equations, in which case it has a more of a canonical form, and you see that this is, apart from the b, this is just the nonlinear pendulum, which is the solution of the vorticity triad, and then this is the gravity wave coming in here. So it's a pendulum coupled to a harmonic oscillator, which in the case of b equals 0 is integrable, meaning exactly solvable. You can write a closed form solution. You just get the pendulum here and you get the gravity wave here. So that means we saw a torus. That means that the solution lives on a 2 torus, and you can think of the fast dynamics going around this way. Of course, it's really in 4 dimensions, so you can't really quite draw this because it should be in 4, not 3. But you have a slow motion going around this way, which is periodic. And you have a fast motion going around this way, which is periodic. But in general, of course, these periods will not be commensurate, because that's a set of measure 0. So they'll be quasi-periodic, and they'll fill the whole torus. That's the classic case of this is the paradigm for an integrable Hamiltonian system. So Ono got with these equations, and actually, because it's a simple system, this is the nice thing about 5 ODEs, he actually implemented this a slaving approach up to like 30th order, and he did it all using a symbolic manipulation program called Maple from the University of Waterloo, which was a better version of Mathematica. And could run these, go up to really high orders. That was really cool. So these are Poincare sections, which Hank has already talked about. So these are cross sections. These are the slow variables. So x3 and phi are the slow variables. They're the harmonic oscillator, and x4 and x5 are the fast variables. And you see you have the pendulum here. You should all know the phase portrait of a pendulum, and the harmonic oscillator here. But as b, this is b equals 0, and as you increase b, you can start that actually for small b, it looks the same. And that's the result of the KM theorem, Kolmogorov-Arnold-Moser theorem, which applies to this system. So theorem says for sufficiently small perturbations, most of these invariant tori survive. So there is chaos. There is chaos in here, but it's hidden in very, very thin layers. But as you crank up beta, B, I should say, larger, then the chaos spreads and spreads. And Ono had quite a sense of humor, so I was never quite sure if this koala bear was real. Right. So but the thing is, because of the KM theorem, you know that actually you can define an exact slow manifold for this problem almost everywhere, at least for the invariant tori. But the invariant tori are almost everywhere. But you do it geometrically. So you know that you just want to pick the middle of this. This is a slow manifold. If I just pick the middle, I can find that. And so he found it. So this is the cross section of the fast variables. I should have added, sorry, x4 and x5. This is he tried to make the fast variables initialize the model. So you set the fast variables to be 0. That's what used to be done in weather forecasting before they had all their time filters. And so what you see, you take a power spectrum here, and you see that this is a frequency going this way. So you see, of course, the pendulum is a nonlinear oscillator. So you see a fundamental plus all the overtones. So the slow dynamics is in this thing. So it's not actually there's no high frequency cutoff because it's a nonlinear oscillation. And you can see the grad wave popping up here. If you go to 12th order initialization and then you run the model forward, you can see that the amplitude of this guy is smaller. So now it's well below the background of the pendulum. And actually he can find a periodic solution, and it's 0. And if you and you can really show it's 0. So this is this cross section, but you can see it's only an asymptotic approximation. I guess you guys know about asymptotic approximations. They diverge eventually. So this was when he initialized at 8th order, he got an amplitude out here. 10th order, he got down to here. 12th order, he got here. But 14th order, it got worse again. And then 16th order, it got worse again. So it diverges. 12th is the optimal for this value of epsilon. But you can actually find a core solution, which is exactly slow. Yeah. Okay, so I wrote this down. So I said that, I have, this is first order. So a divergence is 0. Stream function is equal to height. I can go to first order, and I get, equation for the geostrophic imbalance, equation for the divergence. I can expand this out to 12th order, and I get a really complicated expression. So it's basically going out in this epsilon expansion. I can't even write the equations for you, but it was all done symbolically and turned into code. No room for error. And then you're saying that the fast variable is 0 at time 0, and then you run it forward. Now, of course, if there was an exact slow manifold, if you found it, it would stay 0. But because you haven't actually got there exactly, because it's only asymptotic, so you only get a finite approximation. And so you're setting the fast variable to be as small as you possibly can using this perturbation expansion. But then you solve the full system. This is the full unbalanced system. Yeah. Dimensionality, because basically if you have a slaving relation, then if the fast variables are functions of the slow variables, then you only have a first order in time solution. And if it's a Hamiltonian system with an energy, then it's going to be a periodic. So it's like defined as the. I mean, I don't know about a mathematical, but I just mean geometrically there is going to be a center of this invariant torus. Now, Lorenz in his paper wasn't aware, at least, or didn't seem to. Wasn't aware of the Hamiltonian structure or any of this kind of thing. But he just found that he reasoned that actually that just from a dimensionality that since it's you only have one. It's a 1 degree. I mean, in the pendulum, it's a 1 degree of freedom Hamiltonian system. So that's always a periodic. So he found the slow solutions. He reasoned the slow solutions must be periodic. Therefore, I'll find them as the periodic solutions. Of course, he also found some periodic ones that were mixtures. So that's how he found them, as just seeking the condition of being periodic. Maybe we can. But the Lorentz system is a bit pathological, because the reason that we can find an exact slow manifold is because the slow dynamics is integrable. So we know the answer exactly, and we can get an unambiguous separation between the fast and slow dynamics, at least for almost all initial conditions. There's a set of measure 0 where you can't, because the fast and slow modes coincide, but that's a set of measure 0. Of course, that's not realistic for the atmosphere, because we know that the slow dynamics is chaotic. We have two-dimensional turbulence. So the simplest thing to do, at least this is what with the next student in this line, Joko Uwirzono, I should have said a lot of my students tend to wind up in Britain, because Britain has a very broad view of what mathematics means, which is nice. So Anna is at Leeds and Joko is at Durham. So we just made, of course, you know that the pendulum, if you make the physical parameters periodic in time, then you get chaotic dynamics, because you no longer have a conserved energy. So we just made this Casimir function, rather than being constant, made it periodic in time. The system is chaotic. But there are still theorems that bound this by what's known as adiabatic invariance, and you can show that. So this is going to, again, this initialization. If you go to first order, then you find this is the growth of the action is the amplitude of the fast motion, and it's bounded. And this is versus epsilon. And you can see that as epsilon goes to 0, all these things get smaller and smaller. The first order initialization, the slope is like 1 over epsilon. Order epsilon is the error is epsilon squared, the error is epsilon cubed, and so on. So it really is asymptotic, and this seems to work finite times, even though you haven't got exact invariant tori. So that's dynamical systems. Now then Joko went on to do something even more complex. So this is not very complex, but it's something like a I've forgotten exactly, but it's a simplified version of shallow water with kind of 30 wave numbers by 30 wave numbers or something like that. So it's a largish system from a dynamical systems point. Well, not what Hank was talking about. We're not talking about millions of degrees of freedom, but 1,000 or something. So now what's plotted here is the power spectrum of the potential vorticity. This is a frequency along here, a power spectrum of potential of vorticity, which is in this gray shading. And you can see it's peaked at the low frequencies because it's a slow dynamics. It falls off. It isn't confined just to low frequencies, but it falls off quickly. And the black is the power spectrum of the divergence. And you can see lots of peaks. So the vortical motion has a continuous spectrum. The gravity waves have peaks. Although this is a nonlinear system, but you're seeing the signature, the fingerprint of the gravity waves. And actually, the minimum frequency is 22, and you can see that isn't indeed what the minimum frequency is. But then what you can do is you can initialize, which means try to make the divergence smaller and smaller in the initial state. And these are the same curves then when you for the divergence. If you make the power spectrum for order 1 initialization, order epsilon cubed, and you can see that these fast peaks go away and go to 0. You're still left though with something which is non-zero. That's because the divergence is slaved to the potential vorticity. So these are not gravity waves. This is just the slave part of the motion. But if you actually use the theory to compute what the slave part of the motion is, and you subtract that from this, you get this. This was a different setup. So the minimum frequency is 10. So you can see this is a scale of 10 to the minus 8 compared to 1 and so on here. So you're still able to pick out all these gravity wave peaks from the motion. So it shows that the separation of slow and fast dynamics is possible in these simple models. Well, these are all doubly periodic, and there are resonance kinds of issues and stuff. And actually, this is with Tamom, and there was a lot of this was more formal with averaging and thinking about resonances and all those things. And finally, the last picture I'll show, this is McIntyre and Norton. So this is the real shallow water system. And so what was done here was to use the same kind of theory, but only up to, they went to second or third order possibly. So this is a shallow water system. It's meant to represent the stratosphere, sort of, but this is the potential vorticity field. So you have the pole here, and you have a polar vortex with the wind blowing around it, but it's very strongly deformed. So you're forcing this with Rossby waves, in this case through a mountain, and it creates the wave breaking in this what's called the surf zone. So this is a potential vorticity field at a snapshot. This is the height in the contours and the velocity in the arrows, and this is the divergence at the same time. And you look at this and you might say, well, these are probably gravity waves. But if they derive the height, the height of velocity and divergence from the potential vorticity using one of these balance conditions, you can see that they can reconstruct. Well, maybe it's not so surprising that you can reconstruct the divergence and the velocity, but you also reconstruct to very high accuracy. Sorry, wind and height and wind. You get the divergence field. So actually, these aren't gravity waves at all. These are slaved to the slow the dynamics. And this is actually what did tend to happen in weather prediction some time ago, where to get rid of the gravity wave oscillations that would inevitably arise from errors in the data, you would initialize. So these balance conditions really do work up to a point, even for the PDs. Actually, that's where I'm planning. I think that's all I have. So, oops, yeah. Are there any questions? Yeah.
Does it ever make sense to use different gauge functions in the slaving relation? Instead of having epsilon squared, cubed, fourth, you can have
Oh.
potentials like e to the negative.
Oh, I don't know the answer to that. Maybe there's people in the room that know more about that. No, I don't. I've never got.
If you want different kinds of separations.
Yeah, you can, I guess, like, yeah, you can try to define different regimes. I mean, I guess my, yeah, well, so maybe this is a good time to, my philosophy about, because I'm not a mathematician, my philosophy about asymptotics is that it's a way to make sense of the equations and you build in all the known physical properties. But I'm not really interested in using them quantitatively because I don't think they will be quantitative. I'm more using them as a way of understanding how to look at at a GCM or something. So it's kind of building a theory in terms of the, but that's why it's important to know how to map the different terms onto the primitive equations. If they were unmappable, then you couldn't do that. But everything you do in these simple models has a continuous analog, and you can map it on the primitive equations. So then you know how to think about the cause and effect in the more complex system. But I guess, I mean, there's all sorts of exotica with different powers. But you know, I've always thought, well, if epsilon is 0.3, how do you tell if it's, you know, 3/7 or 2/7 or so? No. Well, uh, the slow manifold. Well, if if the system's steady, then you have an exact slow manifold. So, for example, zonal flow is a solution, or axisymmetric flow. So, actually, there are balance theories of tropical cyclones because it's in a quasi balance. So if it's actually if it has a spatial symmetry, then you can get exact balance. If it's periodic in time, you can get exact balance. But otherwise, if it's chaotic, then no. So I think so. People talk about a fuzzy manifold, the idea that it's somehow, you know, approximately true. Like in the Nekrasov theorem, you have a certain fuzziness which you can bound, and that's good enough. You don't really have to be exact. So I think the I mean, I don't know if there's a proof, but I think if it's a chaotic system, oh, okay, yeah. Well, she worked with Tamam too, didn't she? Yeah. So yeah, but I think it's asymptotic still, isn't it? Right, right, but right, right. Yeah. Okay. So that's not okay. Right. So when I said it doesn't exist, I mean for finite epsilon. I mean, there could be some limit where it exists rigorously as everything goes to zero, as you take epsilon to zero. Whether that's true for the real system, I don't know. But certainly, there was some thought that maybe even at finite epsilon, there was an exact slow manifold. But that's not going to be the case if the slow dynamics is chaotic. Um, and I guess physically, I just think that once you did I? Oops. Once you have a continuous spectrum here, then basically you're overlapping with the fast waves, and there's not going to be any clean way to separate them. But that's very heuristic reasoning. But Brad? Yeah, yeah, because it's on the advective time scale. I mean, of course, there could be other definitions of fast and slow, and you know, you could talk about climate variability where you're averaging over the synoptic eddies or something. So there's, you know, the thing if Hank is talking about, you can. It depends what you treat as stochastically and deterministically. This is all de deterministic. Um, um, Sure, I just forgot the yeah. So if the if your slow timescale is advective, then PV is always advected, unless you had a diabatic process that was somehow very fast. So that's sort of it's the anchor. Um, and we always have Rossby waves. I mean, which are once you put in beta, of course, then this generalizes to Rossby waves. But it's the vorticity. We're usually in a regime where the beta effect and the vortical terms are comparable. So there's not much point really, you know, treating beta separately, except in certain limits maybe. But you always have this slow dynamics. And as I say, in the full system with compressibility, you have the acoustic waves as well as the gravity waves, but you still have this slow vortical motion. Yeah, sorry, just, yeah, Greg? No, because epsilon is the timescale separation. So if you dissipate the gravity waves, that doesn't change the timescale. So that's right. I've forgotten actually. Well, there were maybe even some Lorentz papers, but there, yeah. So there's one approach where you could dissipate the gravity waves, and then actually that's like an inertial manifold, it's called. So if you can think of a mechanism why you would want to dissipate gravity waves, then they wouldn't be on this torus. They would just shrink down like like an attractor. I guess in the atmosphere case, at least, it's not really dissipation; it's radiation, and how do you want to treat that? So I don't think anybody in the certainly in NWP, numerical weather prediction, I don't think people would ever want to use a dissipation that was so large that it would do that for you. So the real, I guess the real reason the things stay balanced partly is just that there's a radiation and then things break in the mesosphere or something. But yeah, you could do that, and maybe in the ocean that's a better approximation, possibly. I don't know. So you could certainly try to add in a dissipative part and make that an inertial manifold. I think Kreis may have. I've forgotten now. Browning and Kreis may have done something like that. But yeah, yeah. I mean, certainly there is a physical idea that the fast waves will get damped faster than the slow waves. Yeah, right. No, I could have. Yeah. Um, and I thought, I mean, I could have, for example, one thing I could have done, if you just show one of the motivations for balance in the atmosphere is if you look at, say, a temperature, a trace of, surface pressure at a station when a front is going through, you don't see any gravity waves. It's like, boom, boom, boom. So you can look at certain fields and you just see that the gravity wave component is really, really, really small. Then, of course, you could do a PV, and actually, McIntyre had some of the earliest maps of PV. Actually, if you look at the Hoskins et al. Paper, there's lots and lots of PV plots there, and they talk about balance in there. I'm not sure people have tried to. Well, I guess yeah, it is applied. I mean, in the operational forecast systems of the 80s, certainly they were doing these kind of schemes on the observed PV. So it is feasible to implement, yeah. But I was keeping it more theoretical here. They do that too. Okay. Oh yeah. Right. So PV is a good variable because it's got coherence and you can follow structures. You can tell if the behavior is physical and you might use it. Yeah. Oh, yesterday. Uh huh. Sure. Yeah. It's sort of true. People look at PV maps instantaneously to get a synoptic evolution. It's quite common. People don't generally look at average PV, but I don't think there's any reason you would. I mean, well, that's yeah. I don't think there's any reason you wouldn't do that. Yeah, well, that's right. But in fact, I should have said that. Good point. For the gravity waves, the PV is zero. So actually, there is a separation, and you don't see the gravity waves in the PV to first order. Um, a few people do. I mean, because all these jet structures I showed are going to show up in the PV. There'll be PV edges. So I mean, I think I'm not sure that people have done it, but you certainly could, and but it would basically be pretty equivalent information. I think largely. Um, well, okay. The thing about energy and momentum is they're single conservation laws, so you have a budget. PV is like an infinity conservation law, so you have to decide, what you want to look at. Actually, I'm pretty sure in that Era 40 atlas there are going to be. I'm pretty sure you could find PV maps there that might be average as well. Um, I guess it's just because in the end, if you I was trying to link it to physical things like storms. I guess we may come back to this a little bit um, tomorrow or Thursday when I'll be talking about the storms from a PV point of view a little bit. But it's true people don't tend to do it in climate too much. Although that's not entirely. I mean, certain people do things. Um, yeah, yeah. There's no. Okay, right. So actually, in this case, we're talking about slow manifold, and as someone already mentioned, you can also do it where you have fast motions. And actually, I think we talked about that case even in this paper here a bit. So, even if you have a separation in timescales is here, the idea is that the fast motion isn't zero, but it's just oscillating, and then you can average over the fast motion. So then you can get equations for the coupling. So you can get equations for coupling between the fast and the slow, at higher orders and things. So it is possible. This sort of classic slow manifold is just for the instantaneous flow to be slow. But you could also look at an average flow when you average over the fast phase, and you can do this using these adiabatic invariance arguments. Yeah. Okay, I think that's time to stop. Thank you.